Hello everyone, welcome to IIT and GATE classes. This is lecture 10 on operating system, and in this lecture we are going to resume our previous lecture only. So just let me revise few points of the previous lecture and then we will start our today's lecture. Okay, so the question was how to implement the critical section, that is known as critical section problem. So how the code will look like if we have critical section implementation. So we have entry section where locking will be done, and then critical section, and then exit section where unlocking will be done, and then we have remainder section which is no use for CS. Okay, so it is not used in critical section, it is just normal code which you have written. Okay, to solve any problem we should have written some code, and that is that code only. So for the only thing is, before critical section there is an entry section which will apply lock. Why locking is applied? So that other if one process enters in its critical section, then other processes must not enter into their own critical section. See, I have told you many times in the previous lecture also that each process has its own critical section. Okay, and when one of the process is in its critical section, then other processes cannot enter into their critical sections. Okay, I think I have explained all these things in the previous lecture only. Okay, so locking is done so that other processes cannot enter into the critical section, and then the process will enter its own critical section, and in exit section it will do unlocking so that other processes can enter into their critical sections. Okay, so I think I have explained the point clearly. Okay, so let me jump to the next slide. If you want to take snapshot, you can take. Otherwise, it's of no use because in the previous lecture itself we have done it. Okay, let me jump to the next slide. So CS problem, I think I have told you. Okay, so the when can we say that critical section problem is good? It is good when following three conditions are fulfilled. But is first is mutual exclusion, progress, and then bounded waiting. So now in this lecture we are going to study the definition, and then we will study how we can implement the critical section problem and so on. Okay, so that means solution to the critical section problem we will see. That means how to implement the critical section. Okay, so yeah, so let me jump to the next slide now. Okay, so first we have to explain the definition of mutual exclusion. ME. ME means mutual exclusion. Mutual exclusion. Okay. So what is mutual exclusion? Mutual exclusion is very simple. It means only one process must enter into its critical section. Okay. Mutual exclusion means, or it means only only one process must enter in its critical section at a time. Must enter in its CS at a time. Okay, so if you want more precise definition, then we can say at any given time. Let me tell you more beautiful definition what mutual exclusion is saying, or you can say when we can say that mutual exclusion is satisfied. So ME is satisfied. ME is satisfied if and only if at most one process is in its CS at a time. Okay, so this is very beautiful point. At most one process. Okay, so if nobody is in CS, that is also good for mutual exclusion. If only one process is in CS, that is also good. Okay, but if two or more processes are present in their critical section, then mutual exclusion is not satisfied, and in that case we will say that race condition has occurred. If you do not know what race condition is, please watch my previous lecture, you will get more clarity. Okay, so if two or more processes, if two or more processes enters into their critical section, then ME is not satisfied. ME is not satisfied, and we say race condition has occurred. Race condition has occurred. So I'm repeating again and again. If you do not know what is race condition and all, please watch my previous lecture. I will not explain it here, otherwise it will simply waste our time. Please take snapshot. I will jump to the next slide. Okay, so this is all about mutual exclusion. It is very simple. Only one process must enter into its critical section, and it is the most basic requirement which we should do. Okay, because if mutual exclusion is not satisfied, then I can say it is not. Rather, it is not exactly critical section. Okay, because in critical section, the basic need was only one process must enter into there critical section at a time. Okay, please take snapshot. I will jump to the next slide. Okay. Yes. So next definition is progress. So this was our first definition, that is mutual exclusion. Second definition is progress. What is progress? Let me tell you. See, for example, we have say 5 processes: P1, P2, P3, P4, P5. Okay, and I am assuming that P1, P2, and P3 they want to enter into their critical section, but P4 and P5 does not want to enter the critical section. Now you may be wondering, sir, how we can say that process wants to enter, so and so on. So let me tell you. So P4 and P5 does not want to enter in critical section. That means that they are in their remainder section. Okay, they are in the remainder section. If you do not remember the remainder section, please watch this. I have told you now, remainder section means it is no use of CS. That means the code which we have written to solve a problem, that code is there. Okay, so we are not for critical section, it is not our consideration. Okay, so you have written say prime number program or anything, whatever way you want, you have written something that is for no use of critical section. That is the basic thing. Okay, yes, just try to remember this thing, that's it. So the code which is not for critical section. So directly I want to say P4 and P5 are in their remainder section, but P1, P2, P3 wants to enter into their critical section. Okay, so this is the basic scenario. So directly they want to they are presently entry section, they are in their entry section. See this, like this, entry section. That means they want to enter in CS now. Okay, that is the basic thing. Okay, so my consideration is I'm just imagining a hypothetical scenario where P1, P2, P3 wants to enter the critical section, but P4, P5 does not want to enter into their critical section. Now, by common sense, you can see decision about who will enter the critical section next must be made considering which processes must be made considering only these 3 processes. Obviously they will not be considered while making decision that who will enter the critical section next. Okay, so progress is very simple. It is saying that decision about who will enter the critical section next must be made considering only those processes who wants to enter into their critical section. That's it. Okay, that is known as progress. So progress means a decision about who will enter the critical section next must be made considering only those processes who wants to enter into their critical section. Okay, and one more beautiful thing is this decision must come in finite time only. Okay, it should not take infinite time, because if it is taking infinite time, then obviously who will enter the critical section next, OS will keep on thinking and so on. Okay, that is not the good case. So by common sense, I think you can see now. If you want me to give a real life example, then you can think like this also. So this is a bus. Okay, and this is a door. Okay, so only one student can enter from the door into the bus. Okay, so imagine this is a bus. Okay, I'm just making a diagram, and there are multiple students. Okay, so some tour is going. Okay, and now teacher is deciding. So there is a teacher. This is a teacher. So now teacher is deciding who will enter into the bus. Okay, so now teacher has to decide who will enter into the bus. This decision must be taken considering only those students who wants to enter into the bus. Na? See, if there is one student who does not want to enter into the bus, or he is not going to the trip. These two are going to the trip, but this student is not going to the trip. So why teacher will consider him also? So decision about who will enter the bus will be made considering only those students who wants to enter into the bus. Na? And obviously this decision must be taken by this teacher in finite time only. Okay, if this teacher is taking infinite time, then nobody will enter into the bus, and obviously trip will not be done. I think you have got it. This is pure common sense kind of thing. Okay. Many students face difficulty while understanding these definitions, but these are very basic and very simple definitions. So I hope I have made the point clear. So let me write the definition. Okay. By the way, I have told you many times, but let me write it so that you get more clarity. So what does progress means? Progress means decision about. Okay. Progress means decision about who will decision about uh, which process will enter the critical section next. Which process will enter critical section next must be made considering only those processes who wants to enter into the critical section, who wants to enter into their critical section, and this decision must come in finite time, must come in finite time. Okay, that is the definition of progress. So you can take snapshot or something. I will jump to the next slide now. Okay, yes. So I'm jumping now. So the next definition is bounded weighting. Bounded weighting. So first of all, many of you will think that weighting, okay, so it must be related to time and all. But actually progress is related to time, because I have told you na, that this decision must come in finite time. Okay, so progress is related to time. Bounded weighting is not weighted to time. It is related to number of processes. Okay, so let me give you some scenario, a simple scenario, then you will get more clarity about what exactly is bounded weighting. Okay, so see, we have P1, P2, P3. Let us suppose we have three processes, and P1 is in, suppose it is in CS. So when P1 is in its own CS, then obviously P2 cannot enter and P3 cannot enter into their critical section, because obviously we have to satisfy mutual exclusion. So I'm considering that P1 is in CS. Now when P1 comes out of CS and again it tries to enter CS, and it got success and it is again in CS. Now again it wants to enter, it got success and it is in CS. Now again it wants to enter in CS and it got success, and so on. Okay, so it is keep on going in and out of CS, but P2 and P3 are never getting their turn. That means bounded weighting is not satisfied. But I am using the word P2 and P3 are never getting their turn. Okay, and it may be like this also. So P1 is going, and sometimes P2 is going into the CS and it is coming out, and again P2 is going, and so on. But P3 is not getting its turn. That is also means that bounded weighting is not satisfied. So even if one of the process is never getting its turn, then we will say bounded weighting is not satisfied. Are you getting it? So I should say like this, that number of processes entering into their critical section after a process request for the same must be bounded. Okay, so for example, P3 has now requested to enter into its CS. Okay, but after P3 has requested, P1 and P2 are going and coming out of CS again and again, and P3 is not getting the turn. That means what? Bounded weighting is not satisfied. Okay, so directly and indirectly, bounded weighting means that when P3 has requested to enter into its CS, then there should be a bound on number of times the other processes can enter into their critical section. Okay, there must be a bound. That means there should be a limit. Like we can say that after P3 has requested, then P1 can go at most 1000 times, or P2 can go at most 10,000 times. That means there should be some bound. Okay, so directly indirectly I want to say that algorithm must be deterministic. Deterministic means you should be by seeing the code, you should be able to predict very well that when P3 will get its turn. Are you getting it? These are very, very heavy statements. If you are not able to follow them, please rewind the video and try to write them all the things which I have told you. Okay, please try to write them. These are very, very heavy words which I have told you. Okay, please try to focus. Okay, so when P3 has requested to enter into its CS, then it should not be like that. P1 and P2 are going and coming into their CS, but P3 is never getting its done. So directly and directly, I want to say there should be a bound on number of processes entering into their CS after P3 has requested for the same. Okay, so there should be some bound on number of times. Rather, I should say like this: there should be a bound on number of times other processes can enter into their CS when a P3 has requested. Okay, I think I have explained you very well. No problem. I know that even if I speak these definitions for even 10,000 times, even then you will not be able to follow them because they are not so easy definition. I will tell you examples only, then you will be able to understand what exactly these definitions means. Okay, so I have just given you definition of mutual solution. Please try to follow it. Then progress. Please try to follow it. And how to check the progress and all, don't worry about. I will tell you all these things in when we will study examples. Okay, and now I have given you definition of bounded waiting. So let me write it properly. What exactly bounded waiting means? Bounded waiting means number of processes entering into their critical section, entering into their critical section after a process request for the same must be bounded. Must be bounded. That is the basic definition of bounded waiting. So number of processes entering into the critical section after a process request for the same must be bounded. Okay, so see this. So bounded waiting is concerned with number of processes. Okay, or rather I can say number of times the processes entering into the critical section after a process request for the same must be bounded. Okay, one and the same thing, no problem. Okay, yes. So now number of processes, do not consider that P1 and P2 there are only two processes. No, they are going and coming, going and coming. So number of processes will keep on increasing. Are you getting it now? So if you have any confusion, then you can write number of times processes entering into the critical section. Okay. So I hope I have made the point clear to everybody. Please take snapshot. I will jump to the next slide. Don't worry if you are not able to follow. Don't worry. It's my guarantee. You will get each and everything once I will jump to the examples. Okay. Please take snapshot. I will jump to the next slide now. Okay. I'm jumping now. So now we will study the types of solution. Okay. Types of solution to critical section problem. Okay. Types of solution to CS problem. So there are broadly three types of solutions. One is software based solution. Second is hardware based solution. And the third is OS based solution. Okay. So there are three types of solution. Software based solution means neither hardware nor OS will help in implementing CS. Okay. Critical section problem means how to implement the critical section. Solution means what? We are actually trying to implement it. Okay. So neither hardware nor OS will help in implementing CS. No one will help us. So obviously software based means what? User himself or herself has to write the code properly. Okay. Next is hardware based solution. Hardware based solution means hardware will help in implementing CS. Will help in implementing CS. How it will help? Don't worry. I will tell you all these things. Don't worry. Implementing CS. Hardware will help in implementing CS. Next is OS based solution. So OS will help in implementing CS. Okay. OS will help in implementing CS. How OS will help and all, don't worry about it. I will tell you all these things. Okay. So here we will study the, I think the most difficult topic according to all the students, that is semaphores. Okay. So semaphores, we will study them in OS based solution. Okay. Hardware based solution, we will study test and set function, Okay, and so on. Test and set function. Okay. Other functions are also there, but we will not study them just to save the time because it is a basic course. It is not an advanced course on operating system. Okay, and software based solution. Okay, let me give you some examples of software based solutions also. Okay, so I will jump to the next slide and then I will show you the examples. Okay, so I think everybody have got it. So there are types of solution to critical section problem. There are three types of solutions. Broadly, we can say three types of solution. First is software based solution, then hardware based solution, and then OS based solution. Software based solution means neither hardware nor OS will help in implementing CS. Hardware based solution means hardware will help in implementing CS. OS based solution means OS will help in implementing CS. Okay. Yes, please take snapshot. I will jump to the next slide now. Okay. Yes, so now let me tell you the software based solution. So we will study four algorithms in four algo in software based solution. Okay. And all these algo will be for two process solution only. Two process solution. Okay. Of course, we have n processes solution also, but we will study that in advanced course. Since it is a basic course, so we will restrict ourselves to two process solution only. Two process solution means we have only two processes who wants to enter into their CS. Okay, so directly, I want to say there are only two processes, P1 and P2, and they want in our system, and we want to implement CS for these two processes only. So P1 is having its own critical section, P2 is having its own critical section, and when P1 is in CS, then P2 cannot enter, and when P2 is in CS, then P1 cannot enter, and so on. So we will study only two process solution. Of course, we have n processes also, P1, P2, P3, P4, P5, and so on up to Pn, and each process will have its own critical section, and how to implement that critical section, that is also there, but we will not study that because this is a basic course. So we will restrict ourselves to two process solution only. Okay. So, and these are very beautiful algorithm and very basic algorithm. You should remember all these four algorithms. Okay. And from these algorithms, I will clear the definition of mutual exclusion, progress, and bounded weighting. Okay. So these are very basic algorithms, and many times in most of the competitive exam, one of these algorithm will come as it is. Okay, one of the algorithm. But of course, by minor modifications and all, they will ask the questions from these four algorithms only. So let me tell you the first algorithm, algo number one. So what they are saying is this is very simple, PI. So we have two processes, PI and PJ. So what PI is saying? PI is saying while turn is not equal to I, okay, CS, and turn is equal to J. And what PJ is saying? See, in GATE exam or in other competitive exam, they will give you just one this code only. So from this code, you can write the other process code also. So for PI, we have written I. So for PJ, we will write J. So same to same. Okay. While turn is not equal to J. CS. And for I, we have written J. So for J, we will write I. So turn is equal to I. So I hope I have made the point clear how you will write the code. So only one, some chances are there that they will give you one code. If both are given, no problem at all. But if they give you only one code, then you can write other code also. Okay, from the symmetry, like PI, then PJJ, then JI. I think I have explained it properly. You have got it. Okay. So for this, you should remember how to write code in C language and all basic languages so that you can follow them. Okay. So with after while we cannot have semicolon, but if we have semicolon, that means what scope of while loop is over here itself. So nothing is there. That means body is not body is null. Okay. So loop body is nothing. So I will say when turn is equal to I, you can think like this. You are it will or control will keep on rotating here itself. Okay, so I can write like this also. Actually, in some books you will see like this blue skip, and then they will apply semicolon. That means what it will keep on rotating here itself. That means a control will not go here, or you can say CS will not be executed. So control will keep on executing this loop only. Similarly, you can write here also do skip. Okay, so do skip is optional. You write or you do not write. So just for the sake of your, you can say convenience, I have written do skip. Otherwise, no use. In GATE exam or other competitive exam, they can apply here semicolon also. Directly they will apply semicolon. Semicolon means control will not go into the CS, it will keep on rotating here itself. So I hope I have made this point clear to everybody. And here they will properly say that turn is a shared variable. Turn is shared variable. Shared variable means both processes, to both the processes, value of turn is visible. Okay, turn is a shared, rather I should say Boolean variable. Boolean variable means it can take only two values, 0 or 1. So you can think like it can take values, only two values, I or j. Are you getting it? Na Boolean variable. So 0 means I, 1 means j. You can consider that also. And since these are algorithms, they are not actual programs. So I should not say like 0 and I how they are matched and 1 and j how they are matched and so on. So you can think like that only. So Boolean means it can take only two values, either 0 or 1. So I can consider 0 as I and 1 as j. Okay. Or if you are not able to follow, you can write here also P0, P1. Okay, and here you will write 0 and here you will write 1 and so on, but it will simply waste our time. And in GATE exam or other competitive exam, you will find these also, P0, P1. They can say PK, PI. Okay, so they can change these letters. Okay, or you can say these characters, they can change. No problem. You should understand the concept. If you are able to understand the concept, then everything is fit and fine. Okay, so now let me start the algorithm. Enough of explanation. Now let me start the algorithm. So turn is a shared Boolean variable. So it can be initialized by I or j. It hardly matters to me. So let me start it has been initialized by I. Okay, so because it is shared variable and it is a Boolean variable, so it has to take some value. So I'm assuming that it has taken I. So this arrow means it has taken value I. So now I will say while see if I say pi, let us suppose pi started first. So I is not equal to I. Is it true or false? I is not equal to I is false. So it will not do. It will not go here. It will simply. So I will say that lock is over. So it will enter the CS. Are you getting it? Now, so this is the entry section. I have told you, na solution will how code will look like of the solution. See this in the previous lecture itself I have told you. So how codes look like: enter section, then CS, then exit section, and then remainder section. So entry section, this is the entry section, okay, where locking will be applied. So this is the entry section. Entry section. Okay, same is the case here, entry section. And this is CS obviously, and this is the exit section. This is the exit section, and here we can have remainder section also. Okay, and remainder section is of no use. You have written the code and all for solving any problem and such like that only. Okay, yes, so now let me start. So when pi came, okay, so I have assumed that turn is I. So since turn is I, so I will say I is not equal to I. So it will obviously it is false. Since it is false, so it will enter the CS. Now assume when pi is in CS, pj can enter or not. Turn was what? I. So I will say I is not equal to j. This is true or false? Yes, 100% this is true. I is not equal to j. So it will keep on doing do skip, do skip, do skip, and so on. Okay, so it cannot enter the CS. Okay, now when it comes out of the CS, turn will become j. So when turn will become j, then and now again pi wants to enter, then j is not equal to I, which is true. Okay, so it will keep on doing do skip, do skip, do skip. It cannot enter the CS. And when control comes to pj, then it will say what we were here now. So the turn value is now j. So j is not equal to j, which is false. So do skip will not be done, and it will enter the CS. Are you getting it? If you still have any doubt, then let me draw the figure, and then you will get more clarity. So turn is a shared variable now. Let me use another color. Okay, so initially turn value is I. I have told you here we have I. So now you can assume whether PI or PJ, whatever process comes first, it entirely decided by OS. Okay, who will come first and all. So let us suppose PI come first. So I will say I is not equal to I. I is not equal to I means this is false. Since this is false, so entry section, that means locking has been done and it will enter into the CS. Okay. Yes. So now when PI is in CS, now PJ can enter CS or not. Let me check it. So turn is I. You can check it out from here. I is not equal to J, which is what? True. Since it is true, so it will keep on doing do skip, do skip, do skip. It cannot enter into the CS. Are you getting it? So you can imagine round robin scheduling and all. So let us suppose, and in CS we can have multiple lines also. It is not like that only one line. It is a section, entire section. So CS can be like this, multiple lines and all. Okay, so while executing, say line number 3, interrupt came. Okay, why? Because say you can assume round robin scheduling and all. So directly I want to say PI is in CS and interrupt occurs. That means what? Round robin scheduling. Because of round robin scheduling, interrupt occurs and control is transferred to PJ. Now what PJ will do? PJ will start from, obviously from here itself. It will say I is not equal to J, which is true. It will keep on doing do skip, do skip, do skip. So for example, time quantum is say 10 nanoseconds. Then for 10 nanoseconds, PJ is not doing any fruitful work. It will keep on doing do skip, do skip, do skip, and so on. Okay, yes. So after 10 nanosecond, control will again come back to PI, and then PI will resume its execution in critical section and all. So once PI has done all these things, then it will do turn is equal to J. So finally, what I will say, now turn will become J. Now, since turn is J, so now you can imagine that after execution of remainder section, you can imagine that, see, it's entirely depends on OS, which process is executing. So I'm assuming that PI is executing. Okay, okay, and please try to focus here. We will try to break the code. We will not try to say that code is correct. We will try to prove that code is incorrect. So you can assume any adverse situation, whatever you want, because I have told you in the previous slide itself, neither hardware nor OS will help in implementing CS. So when OS is not helping in implementing CS, so we have to imagine scenarios and all in such a way that we will try to prove the code is wrong. Okay, don't try to prove that code is correct. Try to prove that code is wrong. Just like tester, if you have done a software engineering, then you have studied testing. No? So testing is done by testing team. Okay, and testing, what testing team is doing? Testing team is not proving that your software is correct. They will try to prove that software is incorrect. Okay, that's why developers and testers, they are not good friends. Okay, just because developer is will try to prove that my code is correct, but tester will try to contradict it, and it will try to prove that the code is wrong. I hope I have made the point clear. Yes, so the basic idea is try to prove. Okay, let me write it. Try to prove code is wrong. Try to prove code is wrong. Don't try to prove code is correct and all. Okay, so imagine all types of scenarios to prove it is wrong. Okay, so imagine all type of scenarios. All type of scenarios. Okay, yes. So finally, what I was saying that when it comes out of CS, then turn will be J. So now see my thinking. I am not saying that control comes to J. I am saying that control is still with PI only. That means OS says that still PI will be executed. So after doing remainder section, it will come back and it will try to enter. So how it come back and all? So you can imagine that there is a while loop here. Okay, so you can imagine that in PI we have a while loop, while one. Okay, so it will keep on executing again and again. Okay, PI will keep on executing, it will never stop. Similarly here also, you can imagine a loop while one, because if there is no loop, then how you can imagine that it has come again and all? Are you getting it? If there is no while loop, then how you can imagine after a intersection again PI come and all? Okay, so I hope I have made the point clear. Or you can imagine like this also, that some other you can say some other user has again started this process PI and all, but that is rarest of the rarest case. Better is you can imagine that we have a while one loop here, or you can say infinite loop here. Yes. So now after doing a remainder section, it come again and it will say while turn is not equal to I. See this. Now turn is J. Why turn is J? Because PI itself has made the turn J. In exit section, it has made the turn J. Okay, so now J is not equal to I. Obviously, it will keep on doing do skip, do skip, do skip, because J is obviously not equal to I. This is true. Okay, so now after some time, control will come to J. Now, I think I have explained you just few minutes back. I have told you turn was initially I, na? That's why I was not equal to J and it was doing do skip and all. So it has wasted the time. But now when control comes to PJ, it will say, okay, now turn is J. So J is not equal to J, which is false. So obviously loop will be broken and it will enter into the CS. Are you getting it? So it will enter the CS and it will execute code line by line and all. Now, when it is executing the code, again imagine control come back here. Okay, and so PI was here, na? Because it was doing do skip and all. So still again turn is J only. So J is not equal to I. It will keep on doing do skip, do skip, do skip. So its time quantum will be wasted, simply wasted, because it is just doing do skip. It is not doing any fruitful work. Okay. So when again control come back to here, so it will complete its execution in CS, and then it will make the turn is equal to I. And once it make the turn I can imagine that control come back here, but I am assuming that it wants to enter again. So if it wants to enter again, now see this turn is I now, so I will make it I. So now I will say I is not equal to J. Yes, this is true. So it will keep on doing do skip. So when control come to PI, it will say, okay, I is not equal to I, which is false, and it will enter the CS and so on. So I think I have explained you all the things. So now you can imagine, see, if now let me tell you the summary of this, you can say code. Let me jump to the next slide. Okay. So now I think I have told you. So you can imagine when initially turn is I, when turn is I. So who will first enter the CS? No doubt I have told you that I is not equal to I and PI will enter the CS. Now you can imagine that first PJ comes. Initially turn is I and PJ comes. So when PJ will come, it will say I is not equal to J. It will keep on doing do skip, do skip, do skip. It will not be able to enter the CS. So PI will enter the CS first. That is for sure. If turn is I, then obviously PI will enter the CS first. So first PI will enter. And now when PI will come out of CS, so I have told you na, in exit section it is do unlocking. So now it has done turn is equal to J. So indirectly PI is saying to PJ, now you can enter the CS because now it's your turn. So when PI come out of CS, it will make turn to J so that PJ can enter. And when PJ come out of CS, it will make turn is equal to I so that PI can enter and so on. So now I think you have got it. So PI, then when PI will come out of CS, now I have told you clearly, turn is now J. Since turn is J, PI cannot enter again. So obviously PJ will enter. So that is for sure. So after PI, PJ will enter CS. Then after that, PI will enter, then PJ. PI, PJ, and so on, like this. And initially, if I imagine that turn was J, then obviously first PJ will enter, then PI will enter, then PJ will enter, then PI will enter, and so on. So this is known as strict alteration fashion. Strict alteration fashion. Okay. So it is strict alteration, na? Like PI, then PJ, then PI, PJ, or PJ, PI, PJ, PI, and so on. Alternatively, okay? They are entering into the CS alternatively. So now let me try to see whether the solution is good or bad. So when can I say solution is good? When three conditions are fulfilled. First is mutual exclusion. Please see this. Mutual exclusion is satisfied or not. So see this. Obviously, when PI is in CS, then PJ cannot enter. When PJ is in CS, PI cannot enter. Okay, so obviously mutual exclusion is satisfied. Now I will tell you how to check mutual exclusion is satisfied or not. So the basic rule is you have to imagine line by line interrupt and try that somehow you try that both process enter into the CS. Is it possible that both process can enter the CS? Let me write it. Line by line interrupt. For ME, you have to imagine line by line interrupt. Line by line interrupt. What do you mean by line by line interrupt? You will get more clarity in other examples or in other algorithm because it is first algorithm. And line by line interrupt means simply turn was I na, so I will say while turn is not equal to I, do skip. So initially turn was I is not equal to I, it is what? I is not equal to I is false. Okay, so it will enter the CS na, but I will imagine since this is one line, so I will imagine the interrupt. After one line I will imagine interrupt and I will jump to here. I will say while turn is not equal to J, do skip. So it will say I turn was I na, I is not equal to J, which is true. So do skip. I will do it only one time, and then I will again imagine interrupt, and I will say okay, it will enter the CS, and then I will again imagine the interrupt, and I will come back to here, and I will say okay, I is not equal to J, do skip. So it will keep on doing do skip and all, and it will keep on executing CS and all. So I think you have got it. So line by line interrupt means after execution of one line, you will imagine interrupt. After execution of one line, you will imagine interrupt. That is the basic way. For example, in PI, after execution of one line, I'm not saying it will enter the CS. After execution of this line, I will immediately say interrupt occurs and control come back to here and all. I hope I have made the point clear to everybody. So mutual exclusion, how to check? You will imagine line by line interrupt. Okay. So now even after imagining line by line interrupt, you can say mutual exclusion is guaranteed. Why? Because these loops itself are mutually exclusive, because turn can be either I or j. It cannot be both at the same time. Now, since turn can be either I or j, when turn is I, then obviously pi will enter the CS. When turn is j, then obviously pj will enter the CS. Okay, so both can never enter the CS, because turn cannot take the value. Turn is a shared variable, na? And it is a Boolean variable. It cannot take the value both I and j at the same time. So obviously, uh, exactly one of the process will enter into the CS. Okay. So the basic thing is mutual solution is satisfied. 100% is satisfied. Next is progress. This is very important point. See, first of all, you should say how to check the progress. So for progress, you have to check processes. There should be some independency. Independent. Independent means, okay. So one process can enter the CS without affecting the other processes. Okay, they should be independent. Let me write it properly. Independent. Independent means pi can go in and out of CS again and again without affecting pj, and pj can enter into the CS again and again without affecting pi. It should happen, but since there is a strict alteration fashion, so I will say there is no independence, so progress is failed. So now let me try to explain the proper definition. Progress, what progress was saying, decision about, see this, decision about who will enter or which process will enter the critical section next must be made considering only those processes who wants to enter into their CS. For example, now see this. You are saying, sir, the code is very perfect. It is very good, but I am saying no, it is not good. Why? Because I have told you try to prove the code is wrong. How I will prove? I will say like this. PI is in CS. Okay, so for example, turn was I. So PI is in CS. Now when PI comes out of CS, it is saying to PJ that turn is yours, so you should enter the CS. Now, what if PJ does not want to enter CS? If PJ does not want to enter CS and PI is saying to PJ that you should enter into the CS, that means what? I am, or that means what? Decision about who will enter the critical section next is not made by considering only those processes who wants to enter into their CS. Okay, so PJ does not want to enter into the CS, but PI is still saying that PJ you should enter into the CS. Okay, what is this? PJ is it's not jabardasti, na? Okay, so PJ is not willing to enter the CS, but still turn is J. So directly indirectly, PI is saying that you should enter into the CS. Okay, and what if PJ does not want to enter CS? So obviously that will create problem for us. Okay, so here progress is not satisfied. Are you getting it? And similarly, PJ, when PJ is coming out of CS, then turn is I. So that means what PJ is saying that PJ is saying to PI, you should enter into the CS. But what if PI does not want to enter CS? So now obviously PJ cannot enter again. Na? Are you getting it? PJ is coming out of CS and now turn is I. When turn is I and if control comes to PI, I will say PI will enter into the CS and all. But what if PI does not want to enter into the CS? PI is in remainder section and all. It does not want to enter CS. Now still it is saying that PI should enter into the CS and all. Okay, or what if turn is I and you can imagine that priority scheduling and PJ is having more priority than PI. So PJ will keep on executing. PI is not getting the turn. You can think or you can imagine scenario like this also. So finally, what I will say, when turn is I. Okay, so when turn is I, then again PJ want to enter CS. No, it cannot enter. So directly and indirectly, please do not get confused. The simplest way to check progress is that when PI is in CS and when it's come out of CS, that if PI wants to enter again, then it should be that PI can enter. Okay, so PI in Hindi, if I want to say, I will say independent chakkar. Okay, so independently chakkar laga paye. Okay, so PI without affecting PJ, PI can enter again and again in CS. PJ without affecting PI, it can enter again and again in CS. Okay, but it is not the case here. Okay, so when PI come out of CS, then PJ should enter. When PJ come out of CS, when PI enter, and so on. So you should remember this thing. Whenever there is strict alteration fashion, progress is never satisfied. Progress never satisfied. When strict alteration, progress never satisfied. Progress never satisfied. Why progress is not satisfied? Because there is no willingness kind of thing. Okay, so PI is saying to PJ, please enter the CS, and PJ is saying to PI, please enter CS. What if they do not want to enter CS? That will create problem for us. So I hope I have made the point clear to everybody. So willingness kind of thing is not there. Okay, so decision about who will enter the critical section next must be made considering only those processes who wants to enter into the critical section. Okay. Yes. So that was the problem. So progress will be never satisfied. Yes. Third is bounded waiting. Third is bounded waiting. So let me check bounded waiting is satisfied or not. So how to check bounded waiting? Let me tell you this thing. So for bounded waiting, I will use the word that imagine one process is in CS. Imagine one process in CS and other process is waiting outside CS and other process waiting out of CS. Waiting in entry section. I should say like this. Waiting in entry section. Okay. Because obviously when one process is in CS, then it has applied some lock. Okay. And other process cannot enter because there was a lock. So now I'm saying that imagine one process is in CS and other process is waiting in entry section. Another process is waiting in entry section. Now, when the process is in CS comes out of CS, then it should get its turn. Okay, the process which is waiting in entry section, it should get its turn, or there should be some bound on number of times the given process which is in CS can enter into the CS again and again. If there is no bound at all, then bounded waiting will not be satisfied. Okay. Now let me tell you. This is very simple scenario. See now, PI is in CS and PJ is waiting here. It is doing do skip, do skip, do skip, and all. So when PI comes out of CS, it will make turn is equal to J. Okay, and when even if PI wants to enter again in CS, it cannot enter. Why? Because turn is J and J is not equal to I. It will keep on doing do skip, and whenever PJ will come get its turn, it will simply enter into the CS. Are you getting it? So when PJ has requested to enter in CS and PI is in CS, then number of processes entering into their critical section after PJ has requested for the same is bounded. And what is the bound? Only big zero. No one can enter into the CS after PJ has requested to enter into the CS. Okay, because even as soon as PI will come out of CS, it's for sure and it's guaranteed that PJ will enter into the CS. I hope I have made the point clear to everybody. So here bounded waiting is satisfied. 100%. Progress is not satisfied, but bounded waiting is satisfied. Because when PI is in CS, if you want me to write, I will write it like this. When PI is in CS, when PI is in CS and PJ is waiting out of its CS, PJ is waiting out of its CS, then it's guaranteed. The word is, I'm using the word guaranteed. It's guaranteed that PJ will enter next. PJ will enter into the CS next. Hence, I will say bounded waiting is satisfied. If it was not guaranteed, or I can say PI can enter again and again, and still PJ is waiting, so now there is no bound. Now I will say that I will apply the reverse process. I will say that OS will help PI because I want to break the code. Now I will say OS will help PI, and PI will keep on executing again and again, and PJ will never get its done and all. Okay, so that will create problem for us. So the basic thing is, imagine one process is in CS, another process wants to process is waiting in its entry section. So when PI comes out of CS, then it is guaranteed that PJ will enter into the CS. That means PA cannot go in and out of CS again and again, even though PJ is waiting out in its entry section. It is not like that. If it was like that, then I will say bounded waiting is not satisfied. Okay, anyway, I will tell you all these things in more detail when we will start other algorithms and all. Okay, please take snapshot. I will jump to the next slide. Okay, so yes, so here we have studied mutual exclusion satisfied, progress is not satisfied, bounded waiting is not satisfied. Sorry, bounded waiting is satisfied. So directly and directly solution is not good. It is not good solution. Why it is not good? Because I want that all the three properties should be satisfied properly. Okay. So now let me start the next algorithm. Okay, please take snapshot. Yes. Okay, so now let me tell you algorithm number two. Okay. So what algorithm number 2 is saying? Algorithm number 2 is saying we have a flag. It is an array of two elements 0 to 1. Okay, that means flag 0, flag 1. And that is also of Boolean type. So code of PI I am writing. So similarly, we can write code of PJ also. PI code is while flag J. While flag J, flag I is equal to true. And then CS. And then flag I is equal to false. Okay, that is the code of PI. And then we will have remainder section and all. That is of no use for us. So now I will write code for PJ. So code of PJ will be simply, okay. So for PI, we have written JII. So for PJ, I will simply replace them. Okay. So what I will do, let me copy it. Let me copy it just to save the time. Okay. So I will simply change it. Okay. So what I will say, so I will make it as I. Since here it was J, so I will write I. Since here it was I, so I will replace it by J. Similarly, I will replace I by J. I think you have got it. So how we will do all these things? Okay. So I am repeating again and again. In GATE or other competitive exam, they will give just one code. So you can copy that code. Okay. So simply replace I by J and J by I. You will get it. Okay. So finally, this is the code. So now we have to check all the three conditions are satisfied or not. And since flag is an array of two variable, and these two variable are of Boolean type. 0 to 1 means what? Array 0, flag 0, flag 1. So 0 means I, 1 means J. You can imagine like this. Okay. So flag I, flag J. So these are two variable and these are Boolean variable. They can be either true or false. Okay. So now how we will look into it. So let me tell you. So we will say, okay, so we have to consider the three situations. And by the way, there are actually four cases here. Okay, so you can imagine this flag I, flag J. They can be either both 0, 0, 0, 0, 0, 1, 1, 0, 1, 1. Okay, let me write it. Flag I, flag J. Flag I, flag J. So either they are 0, they are 0, 1, 1, 0, or 1, 1. So let me write it for case number 1. Let me solve case number 1. That is both are 0. When flag I, flag J, both are 0. So now we have to check the first condition, that is mutual exclusion. Mutual exclusion means uh, both should not enter into the CS. So now you can imagine a PI, what PI will say, check flag J. Flag J initially is 0. So it will say while 0, obviously 0 means false. So loop is broken and it will say flag I is equal to true. Flag I true means what? It is saying that now I'm going to enter into the CS. Okay, so let me make a story first. So PI is saying while flag J, that means what? If J wants to enter CS, then I will not enter. It is saying like that. And then if J does not want to enter CS, then it will say, okay, I'm going to enter into the CS. Then it will enter into the CS, and then it will say, I'm not waiting to enter into the CS. That means I have come out of the CS. So PJ is saying what? While flag I. That means what? If PI wants to enter CS, then I will not enter. Okay, so they are just compromising. PJ saying while flag I. That means if PI wants to enter CS, I will not enter. Okay. Now imagine if PI does not want to enter CS, that means flag I is 0. Then loop will be broken and it will come out of it. That if see if PI wants to enter CS, that means what? Flag I will be 1. Flag I will be 1. So while 1 means what? It is infinite loop. So it will keep on rotating here because there is semicolon. Na? So it will keep on doing do skip, and all. You can think like that only. Okay. So while after while we have semicolon means what? It will keep on rotating here itself. Okay. So now flag I am assuming that PI does not want to enter CS, then PJ will say, okay, now I am going to enter into the CS. That's why it is saying flag J is equal to true. And then it will enter the CS. And when it come out of CS, it will make flag J is equal to false. That means now I do not want to enter CS or I have come out of CS. That is the basic story. So story, I think you have got it. PI is saying if PJ wants to enter CS, I will not enter CS. It will say, okay, I'm going to enter CS. It will enter CS. It will say, okay, I'm out of CS. Same is the scenario here. PJ will say if PI wants to enter CS, I will not enter CS. It will say, okay, flag is equal to true means okay, now I'm in I'm going to enter CS. It will enter CS and it will say, okay, I'm coming out of CS, or I have now I don't want to enter CS and all. Like this you can make the story. Okay, so now we have to check mutual exclusion. So now you will say, sir, see, pi will check flag j is 0. Yes, it will say, okay, flag I is equal to true, it will be in CS. Now when pi is in CS, pj can enter CS. It will see this immediately. See, flag I is true now. Okay, let me write it. So this is I and this is j. So flag I, flag j, both were 0. This is the case number 1. Now it is checking flag j. Flag j is 0. See this, flag j is 0. That's why it will say flag I is equal to true. Flag I true means what? I will become 1. Now I will become 1. Now it will say it will enter into the CS. Now since it is in CS, now see, this pj can enter into CS or not. It will say while flag I is what? 1. Since flag I is 1, so pj will not enter CS. So you will say, sir, mutual exclusion is satisfied. But no, I have told you in the previous example also, line by line interrupt you have to imagine. So try to imagine line by line interrupt. Okay, so I will say initially both are 0. Okay, so yeah, so let me draw it again. Initially both are 0. Initially both are 0. So I will say pi, it will apply this loop while flag j is 0 na. So obviously loop will be broken. Now I will don't say that control come here. I will say immediately interrupt comes and control shifted to pj. Are you getting it? That is the basic meaning of line interrupt. So while flag j, loop is broken, control is shifted to the pj while flag I is also 0, loop is broken. Now it will say flag I is equal to true, loop is broke. One line is executed, so control is shifted to the next process. It will say flag j is equal to true, then control will shift it to the next process. It will enter CS, and then control will shift to the next process. It will again enter into the CS. So both processes will enter into the CS at the same time. Mutual exclusion is not satisfied. I hope I have made the point clear to everybody. So here, even mutual exclusion is not satisfied. Now, since mutual exclusion is not satisfied, that was the basic necessity. So no need to check progress and bounded weighting. Okay, I'm just leaving that because basic necessity, that was a mutual exclusion, it is not satisfied. So just leave that algorithm. That is not good solution. I will simply say it is not good solution. Okay, so case number 1, not good. Not good solution. Why? Because even mutual exclusion is not satisfied. Okay, at least mutual exclusion should be satisfied, na? Because when both process will enter into the CS, then obviously the basic aim of making CS, the basic aim of building CS is now broken. Basic aim was that only one process should enter into the CS at a time, or but here multiple processes are entering. That will create problem for us. Obviously race condition will come, na? When mutual exclusion is not satisfied, race condition will come. Okay, so I hope you remember what is race condition and all. Okay, now so you can take snapshot or something. Okay, and that's all for today. So in the next class we will start the other cases. Okay, that means 0 1 1 0 and 1 1, all these 3 cases we will discuss them in next class. Okay, so it's my request to all of you, please try to do yourself all these 3 cases. Okay, and then we will jump to next algorithms and all. Okay, then thank you so much. Bye bye.